Hi, in this video we will be talking about exploring and analyzing the Luftdaten, or as it is now called Sensor.community, particulate matter measurements with low-cost sensors. Here you see a map of the active Luftdaten sensors around the world. It is a global network and community operated by citizens. The community of involved citizens and cities keeps on growing, although the center of gravity is clearly located in the EU. The link with vacuums is that Luftdaten uses the SDS 011 PM sensor. These low-cost PM measurements lead to various questions from citizens like, how can I compare my own measurements to the official measurements by the Flanders Environment Agency? Or, how well do my sensor measurements compare to the official ones? And is my local situation better or worse? Can I use my own measurements to support such claims? Here you see an illustration of the measurement cycle of the SDS 011 in Luftdaten or Sensor.community. The PM sensor is switched on and off by the software, the firmware of the microcontroller, the Node MCU ESP8266, in order to extend its lifetime. This leads to a true measurement phase of about 20 seconds on, followed by almost 2 minutes off. Optionally, one can also attach a module like the DHT22 shown here to measure relative humidity and temperature. We would like to have a way or a method to easily combine and compare the low-cost sensor measurements to the official ones of the Flanders Environment Agency. For this we use a tool called Luftdatenpumpe in German, which translates to a pump for Luftdaten. We can use it to pump data around. Luftdatenpumpe is a free open source software tool developed by Panodata that does the automatic retrieval of all Luftdaten measurements, both real-time but also from historic backlog CSV, as well as official measurements from the FEA. It combines these two data sources into local databases, like the one shown here, Postgres and Influx. And on top of these local databases, visualization exploration is done mainly by Grafana, but other options like R and Shiny are possible too. So now we have a tool or website which allows us to explore the combined information from our low-cost sensors and official measurements. We will now give a short demonstration of the main capabilities of this website and tool for exploring and analyzing the sensor measurements.
As mentioned earlier, the main software used to harvest, store and combine the measurement data for all the particulate matter Luftdaten sensors active in Belgium and the official measurements is called Luftdatenpumpe, in short LDP, hence the name of the URL of this website. LDP mainly uses Grafana for the visualization of the data, and much of the dashboards and functionality we will show were developed for us by Panodata, who are also the authors of Luftdatenpumpe. Warning: what we're about to show is to be considered as a showcase of the possibilities and not a final and polished product. The landing page of the data portal shows two panels with hourly PM2.5 concentrations, that is, particulate matter with a diameter up to 2.5 micron. On the left side, the dots represent the official measurement stations in Belgium measuring PM2.5. The upper part is Flanders and shows the VMM measurement stations. On the right side, you see a much denser number of dots. These are the currently active Luftdaten PM sensors in Belgium. You can clearly see that they are concentrated mainly in Flanders and Brussels. Currently, the total number of active sensors is around 800. The color of these dots represents the measured PM2.5 concentration and ranges from blue, low concentrations, to red, high concentrations. It is already interesting to see how the picture of the colored dots on the left agrees or disagrees with that on the right. Also, as we start to zoom in on the right, we see that some sensors clearly deviate, have a different color to the majority of the surrounding ones. This could already be an indication of a very local event or of a malfunction. Now the user has two options. If the user clicks on a colored dot in the left panel, then the Luftdaten sensor closest to this official measurement station is looked up and automatically chosen for comparison. Likewise, if the user clicks on a colored dot in the right panel, then the official measurement station closest to the chosen Luftdaten sensor is looked up automatically for comparison. Let's now demonstrate such a comparison by choosing a dot on the right side. After clicking on a colored dot on the right side, we arrive at this page. First of all, we see here in this panel the location of the sensor we clicked on, the orange dot here. Besides it is shown the location of the nearest official measurement station of the Flanders Environment Agency. Now we are presented with a range of new graphs and plots comparing the Luftdaten PM sensor measurements to that of the nearest official measurement station. By default, the comparison is made for the past 30 days. This first plot shows the time series. The orange line represents the official measurement station and the gray line the sensor. From this we can better see and compare the behavior over time. In general, the sensor measurements are lower than the official measurements. The most of the time it does seem to follow the trend quite well. Even though the sensor and the monitoring station are not at the same location, on average we would expect a good agreement. Deviations, however, are possible due to influences from local sources like wood burning. The graph immediately below shows the ratio of the sensor to official VMM measurement. In the ideal case of near perfect agreement, we expect to see a line here close to 1, the green line, the whole time. But here we also see that our sensor underestimates. In other words, the ratio is lower than 1 and sometimes has spikes much larger than 1. Since we know that particle growth co-depends on relative humidity, in the background of this graph, the variation in relative humidity over time is shown as a filled blue area and labeled on the secondary y-axis on the right. There does not seem to be a clear relation between higher relative humidities and overestimation. The next graph shows the agreement between the official measurements of VMM on the x-axis and that of the sensor on the y-axis as a scatter plot. The gray diagonal is a perfect agreement one-on-one line, and we see that the sensor measurements fall below and above the line. Here the colored dots represent the relative humidity, with blue representing low humidities and red high humidities. So after zooming in, we see it is a bit of a mixed bag, as we see underestimation when the relative humidity is both low, blue dots, and high, red dots, and everything in between. In the case of overestimation, it looks like it occurs more at high relative humidities. And we even have more ways of representing the data. Another way of representing the data is shown at the top left, where we present the daily PM2.5 mean concentrations in a calendar plot. Each dot represents one day, and the red dot is shown when the daily mean exceeds a given threshold, here set at 25 micrograms per cubic meter. The top right summarizes the number of exceedances above a given threshold for this year for both the sensor and the official measurement station. For example, the sensor recorded 34 days with the average above 10 microliter per cubic meter, while the official measurement station recorded 69 days. Below the calendar plot, the distribution of measurements is shown in a histogram. The gray one is for the sensor, and the orange one is for the official measurement station. This other graph shows the distribution of the sensor measurements as a function of the relative humidity. At both extremes, at the low relative humidity and the very high relative humidity, there are fewer measurements. This colored strip at the bottom allows for a quick visual comparison. Each hourly measurement is represented here by its color code. The resemblance of both strips is a measure for the agreement between the sensor and official measurement station. In general, we see that the color strip for the sensor, the one at the top, is bluer or more blue than the one of the official measurement station. In other words, a visual cue for the underestimation of the sensor. We also have a CSV export functionality, but we won't show it in detail. Just know it is there. Now, let's go back to the top of the page. Until now, we have shown visualizations for comparing the sensors and official measurements agreement and disagreements in different ways. But what about correcting the sensor data? Well, we have implemented several algorithms from authors like Chakrabarty. Let's demonstrate this feature using Chakrabarty's correction algorithm. In this screen, we are presented with the correction formula being used, in this case, the one of Chakrabarty. The correction, or growth factor, is here a non-linear function of the relative humidity RH and has two fitting parameters, A and B. The current values for A and B are shown at the top, here A and here B, with also a maximum allowed value for the growing factor, here set at 1.5. The calculated correction factor is applied and shown immediately in the different graphs. Here, orange is again the measurement of the closest official measurement station. Gray is the original uncorrected sensor measurement, and black is a corrected sensor measurement using Chakrabarty's algorithm. Let's zoom in on some parts. Here we see that after applying the correction for the growth factor, the black line seems to be in better agreement with the official measurements in orange. This is illustrated by the time series, the scatter plots, and the colored strips. We do want to note that the relative humidity used in this correction factor is the one measured in the official measurement station of VMM, and not the one measured with some low-cost relative humidity and temperature sensors. Of course, there is still quite some room left for improvement, certainly in the choice and optimization of the parameters A and B. This is where one final functionality called LDPR comes in handy. Here we went a step further and implemented a feature that automatically calculates the regression, correction, fit parameters for a given relationship by using humidity in R and Shiny. After clicking on the LDPR button, the data range that was visible in Grafana is automatically passed on to the R Shiny application for further analysis and correction, like as shown here, an automated regression and fit of a given non-linear function. The graphs below show the results on the left without correction and on the right with correction. Here we see that the results improve after correction as illustrated by the higher R-square. Still, the overestimation or the positive bias remains. So, this concludes the illustration of the main features of the data portal to visualize, compare and correct Luftdaten measurements to those of official measurements of the Flanders Environment Agency.
So, this concludes our presentation. To summarize, we have demonstrated a tool or website that harvests and combines sensor and official measurements. Exploration of the sensor data is easy and in near real time thanks to Luftdaten. A visual overlay and automated comparison with official measurements is possible in Grafana. And we can dive deeper into the data and try different algorithms in R and Shiny.